Hi everyone, I'm Chelsea Finn. I'm a PhD student at UC Berkeley. I'm going to be talking about guided policy search for deep robotic learning. Before I talk about guided policy search, first I'm going to talk about deep learning. So there's been a number of success stories in deep learning for speech recognition, object detection, and machine translation, to name a few examples. And the reason why people are so excited about deep learning for these sorts of things is that it works. And in particular, one, it can handle raw sensory observations, so it can map directly from the raw audio wave and the raw pixels to the output that you want. And second, it scales to the diversity of the real world, so that there are systems that are using deep learning that are deployed in the real world that you can like talk to your phone, for example, or upload your own picture. And these systems will work on those settings, and it can scale to the diversity of user-provided images and user-provided speech. Okay, but what about deep learning for decision making? Well, there's been a number of success stories in deep reinforcement learning for behavior. And here's a few examples. So some great work at DeepMind showed how we can learn how to play Atari from raw pixels. Some work by my colleague John Chilman at Berkeley showed learning behavior, walking behavior, locomotion, and simulation, and also some other work by DeepMind on learning simulated manipulation skills. But one of the big challenges with all these methods is that they're all in simulation, and all of them generally require on the order of millions of time steps of experience if you want to be able to learn these policies. And so how can we get efficient algorithms for learning in real-world settings? If we want to apply these in real-world settings, we wouldn't be able to practically run them because they would take on the order of weeks or months of experience in order to learn. And so that's where guided policy search comes in. So in this presentation, I'm going to be talking about guided policy search. First, I'll talk about what the method is and what we can achieve with it, and then after that, I'll be talking about the open source implementation and kind of what's in it, what components are there, and the way that we designed it in order to make it more easy to build on top of for future research. Okay, so the main ideas behind guided policy search is first we're going to decompose the problem that we're trying to solve into different subproblems, and then solve each of those subproblems with optimal control, which is very efficient, and much more efficient than reinforcement learning algorithms like Q-learning or policy gradient. And then the last key idea is that once we have a solution to one of these subproblems, we can actually train a function approximator like a neural network, some very flexible function to map from raw observations to whatever raw output that we want across the subproblems. And the way that we're going to train that function approximator is using supervised learning. Because we know how to train neural networks with supervised learning, and generally it's very effective and more efficient than trying to apply a reinforcement learning algorithm directly. Okay, so how does this work? So say this is a robot, and we want the robot to be able to insert the red block into the corresponding hole for the shape-sorted cube. So here is starting from scratch. It doesn't know anything about the world, doesn't know anything about its arm. All it knows is that it's getting feedback. It's getting feedback in the form of a cost function for how close it is to reaching its goal. And then over time, it's able to learn how to solve the problem. And the way that it does that is the way that we're decomposing this problem into subproblems is that we're saying each position of the shape-sorted cube is one subproblem, and we can use a very efficient trajectory-centric reinforcement learning method inspired by optimal control to solve that subproblem and do that for each of the subproblems. Okay, so those are the main ideas. What does the actual algorithm look like? So here's a simplified overview of what the algorithm looks like. First, we initialize the policies for each. We initialize local policies for each subproblem. In practice, these are time-varying linear Gaussian distributions. So they're fairly simple policies and not super expressive, so they won't be able to solve the entire problem, but they can solve these subproblems. And then we iteratively first collect samples from each local policy. So you saw that in the video. The robot was collecting data for each position of the shape-sorted cube. Fit a local dynamics model for each subproblem. And the reason why it's local is that generally fitting global dynamics models is very hard, and it's going to be inaccurate in places where you haven't seen data. But instead we're going to assume that we're going to just fit a dynamics model local to the trajectories that we saw for a single condition. Then we're going to update our local policy using optimal control. And we're not going to fully solve for our local policy because our local dynamics are only going to be accurate within near the trajectory that we saw day before. So we're just going to take a step on, in practice, a second order step on updating that local policy. And then we're going to train the global policy to match all of the local policies. And here the global policy is the neural network. So it's much more expressive than the local policies, and it can match what they're doing in different scenarios. Okay, so this is what the algorithm looks like. Any questions on that? Okay, and mathematically this can be formalized in a number of ways. People have shown that you can formalize it using dual gradient descent, BADMM, mirror descent. In practice, what we're using the most often right now is the mirror descent version of this. BADMM, so ADMM is an optimization method, alternating direction method of multipliers, and the B means that we're going to use a Bregman divergence. Okay, so what we can do actually with this algorithm is that we can make the neural network be a convolutional neural network that maps directly from the images that the robot sees to the torques at the joints. And so each of the local policies actually only gets the robot state as the state of the shape-sorting cube, whereas the global policy does not get the position of the cube, and it instead gets the image. So it's forced to learn both vision and control. And using this convolutional neural network architecture, we're able to learn visuomotor skills that directly map from pixels to the torques on the robot's arm for skills like inserting a block into a shape-sorting cube, putting the claw of a toy hammer underneath a nail, as well as screwing a cap onto a bottle. And we're able to do these all in the real world in a realistic amount of time. So without vision, we're able to learn skills on the order of tens of minutes, whereas with vision at this time, when we did this about 2 years ago, we were able to learn in about 2 or 3 hours. But in practice with the latest GPU technology, I suspect that would be closer to on the order of 1 hour. Okay, so this is great. We can learn behavior from scratch, and we can learn behavior that's mapping from raw observations like pixels to torques for skills, complex manipulation skills on a robot. Yes?
That's the part that the convolutional layers extract the features of the picture, and then you feed into the connected layers.
Yep.
And you extract the configuration from the connected layers. And do you think the power of control is from the feature extraction or just the connected layer?
So to perform this task, it needs both the vision aspect of the network as well as the control parts, because it needs to know, for example, in this case, where the shape-sorting cube is. And so both parts of the networks are important. In practice, in the supervised learning phase, we backpropagate all the way to the pixels. We also include the robot configuration, which is just like the joint angles, the pose of the gripper, concatenated with the visual features. And so I think both aspects of the network are important. Does that answer your question? Okay. Okay. And so beyond this initial work, this work, the initial code base was written in MATLAB and had a lot of issues with it. And since then, we've re-implemented the code in a Python-based framework using ROS with the robot. And I'll talk more about the code base later, but since then, there's been a lot of research that's built upon the initial method. So I'll outline some of those methods here, and everything with an asterisk either use the code base when it was initially done, or it is currently implemented in the code base if it happened before the code base was released. So first is some follow-up work that I did on using a learned state representation so that we can manipulate free-moving objects, like lifting an object with a spatula. Recently, there's been some work at USC by Yevgen and others on learning to play hockey, and kind of the benefit and the improvement that they made with this method is they can handle more discontinuous dynamics and more discontinuous cost functions. There's also been some work at Google on making an asynchronous version of guided policy search, such that you can run training across many, many different robots where each robot gets a different door, and each door is in a different position, so that you can learn how to generalize across different door positions. There's also been some follow-up work on transfer learning, so transferring across robots and transferring across different tasks. Trying some work at UW on allowing the network to be on policy, so you can sample from the neural network rather than sampling from your local policies. It can also remove the need for deterministic resets, which is important for learning the local dynamics model. And lastly, there's also been some work on Google that has used this method for imitation learning, where there was a demonstration from a human on pouring or opening a door, for example, and they were able to imitate that using reinforcement learning once they learned the reward function. And then beyond robotic manipulation, there's been a number of follow-up works in other areas. For example, there's been some work on, before I go on, there's also, beyond the 6 things that I highlighted here, there's also has been work on inverse reinforcement learning, semi-supervised reinforcement learning, also policies with memory, which could be important for different robotic tasks. Yeah.
In your research, you use only vision as your input data, or you also use sensors to detect the weight of the book?
So in practice, all of these methods have optionally used vision and have used proprioception of the robot arm.
In your previous demo, you only use vision?
You're only using vision and proprioception of the arm, so where the arm is in space.
And in this, how about in this?
In all of these works, these are using the same. Some of them don't use vision, but yeah, all of them are using those. In general, haptic sensing and force sensing is, I guess, an interesting direction for future work. Generally, getting good haptic sensors that don't break all the time is challenging. Yeah, and also because most of these are actually using torque control on the joints, which actually gives you some form of torque sensing, because you can actually apply a torque and then see where you're at.
Suppose that the machine knows that the existence of, for example, weights.
Okay, and so beyond robotic manipulation, there's been work on, well, this is also manipulation, but using a hand. So this is some work that was done at UW. There's been some work at NASA on tensegrity robots. So this is called the Super Ball robot, and they use guided policy search to learn how to roll this ball. Because this particular robot is very tricky to control with manual control, and so learning-based approaches are very promising for learning how to roll in this case. There's also been some work on mobile robots. So in this example, having a quadrotor fly through a forest, or later it'll show it flying through a hallway. And then beyond robotics, this method has also been applied for in a meta-learning scenario, so learning how to optimize a neural network. It also could be framed as a policy search problem. And then lastly, there's also been some work on doing data imputation with guided policy search. So in this case, it was filling in missing parts of the image, as you can see in the figure. Okay. So kind of just in summary, there's been a lot of research just in the past 2 years, and I think the research is picking up. And there's also been work on guided policy search at a couple startups and companies that are using the code. Here's some of the GitHub statistics, and then I just checked some over the past 2 weeks. There's been around on the order of 300 unique visitors and 30 unique learners. Okay, so what's in the code base? The first decision that we made when we were releasing this code is we included both the algorithm as well as the agent interface, because a lot of the work in robotic research and reinforcement learning research is actually how do you actually interface your algorithm with the agent, with a robot, with a simulated robot, with an optimizer. And so we wanted to also release our interface for interacting with the agent so that other people could use that and more easily build upon the algorithm. And we also wanted it to be, I guess our first design decision was to decouple the agent and the algorithm, because we wanted people to be able to run guided policy search on their own robot in a fairly easy way without having to modify aspects of the algorithm. And in fact, people have added their own agents. So actually, the startup that I mentioned before, they're using a universal robot, a UR10, and they added an interface for between guided policy search and their UR robot. The second design decision was having separable modules for different parts of the algorithm. For example, dynamics fitting, the optimal control phase of the algorithm, supervised learning, and the cost function. These are all different modules, and it allows a user, if they want to kind of research one aspect of the algorithm and switch something out for their own purposes, then it should be easy to do that. For example, some of the work on the hockey playing is swapping out a trajectory optimizer primarily, and in order to get more effective performance. And we've also swapped out different deep learning libraries in the supervised learning aspect of the model, and then you may also want to handle different cost functions for different tasks. Yeah, and so we want to make it easy to make modifications to the individual modules. And then lastly, one thing we really wanted with this code base is we wanted, in general, in deep reinforcement learning and in machine learning in general, there's a lot of different hyperparameters, especially in a complex system like this, where there are many different aspects of the algorithm. And so we wanted all of the hyperparameters to be editable in one place so that you could very easily tune things and tweak things without having to go into individual files in the code base. And kind of the goal here is we want it to be easy to iterate about different versions of an algorithm that you may have. And then lastly, so the different agent interfaces that we have implemented are Majoko, which is a closed source physics engine, ROS with a PR2, Box2D, which is an open source physics simulator, and as I mentioned before, the universal robot, which is an open source contribution. And then on the deep learning, on the policy optimization side of things, we currently support Caffe and TensorFlow, which allows for, Caffe is something that's very widely used in industry and very easy to, and simple to get started with, and TensorFlow enables a bit more flexibility and is also very well supported by engineers at Google. Okay, so kind of how do you get started with the code base? We, at this URL, we have the installation instructions and starter examples for each of the different types of agent interfaces. For example, we have a starter example for moving an arm in 2D in Box2D. In Majoko, we have a peg insertion example of a robot trying to figure out a 7-degree freedom arm, trying to figure out how to insert a peg into a hole. And then we also have an example that you can run on a PR2 in Gazebo, or if you have a PR2, you can run it on a real PR2. And kind of, well, the reason for the simulated interface is that a lot of times you don't want to necessarily iterate in the real world because real world experiments take a lot of time. But with a 7-degree freedom arm in Majoko, for example, you can iterate on a problem that's equally or similarly complex as the problems in the real world with a robot like a PR2. Okay, so kind of just one glimpse into the code. I don't want to put up too much code, but this is just the main function that runs things. This is what the code looks like. Essentially what this is doing is just initializing, collecting samples, so just taking samples from the agent. Down here, taking a step up the algorithm, that's what take iteration does, and then logging data. We really wrote the code for it to be readable so that people could understand the algorithm, and because it is a fairly complex algorithm, we want it to be somewhat easy to digest the code. We also have a GUI for tracking progress and visualizing behavior, and I think this is kind of something that's generally important. If you have a decision-making system, you want to, one, be able to see how it's doing at any given time point, but it's also useful to see actually like what the behavior looks like. So this is a visualization of the trajectories that it took at this current stage of learning, so that you can actually kind of keep track of what it's doing.
So what's the difference between TensorFlow and visualization?
TensorFlow? TensorBoard. So we actually wrote this before TensorBoard existed. I think that it definitely could make sense to hook up something like TensorBoard. You could put the image visualizations in TensorBoard's image visualizer, and likewise for the different quantitative metrics that you want to evaluate. And that could make a lot of sense.
Thank you.
Okay, and so with that, I'd like to thank well, in addition to myself, here are the core developers of the codebase, Justin, Marvin, Harley, Dennis, Emily, and Sergey. And beyond that, there's been a number of open source contributors that have contributed and added to various parts of the codebase. For information and documentation on the code, that's the first link, and for the second link is actually where the code lives right now. I'd also like to throw in a short plug for the deep reinforcement learning course that I'm co-teaching this semester. Almost all the materials for that course are online and available, so if you're interested in learning more about the algorithmic details and just generally different algorithms in deep reinforcement learning, you can check out the information there. And I would be happy to take questions. Thank you.
What are the number of parameters and the kind of parameters that will need to be tuned depending on different examples or problems that you're applying this algorithm to, and how maybe difficult it is?
Yeah. So I think that there's generally, I guess, depending on with the latest versions of the algorithm, we actually kind of reduce the hyperparameters that you need to look at. And generally, I would say there's maybe two kind of key hyperparameters. The step size, which is pretty common in any machine learning algorithm, and the initialization, basically kind of the initial controller.
What about the dynamics or basically the like you have inside Cadir? I think it was based on a Gaussian model, right? So you have to maybe choose the number of components, but maybe it's not so sensitive to that. I don't know.
Yeah, so the dynamics model is a locally linear model that uses a Gaussian mixture model prior. And in practice, we found that we haven't needed to tune the number of mixture components for the problems that we're looking at.